Okay, so now a proposition. Well, first, uh, given t not different to 0 and p greater than 2, then there exists, let's say, f in L2 in Rn such that um, E I T naught population applied to F is not in LP Rn. Okay, so if F is in L2, then when we apply this operator, um, this F, when applied, it is going to be in LP, P greater than 2. Okay, and another one, let S prime greater than S positives and F is in HS Rn, okay, such that F is not in HS prime. Okay, then for all t real number, we will have that EIT population F is going to be in HS and EIT of F is not going to be in HS prime. So we can say that in some way, if this F has HS or S regularity but not S prime regularity, we are asking to have more derivatives in this space, and the operator maintains the same regularity. It's going to be in HS but not in HS prime. Okay, so to prove the first one, it is enough to choose G in L2 or N such that G is not in LP. Okay, and if we take F equals to E minus I T naught of G, this will be the definition of F, then F is in L2 because of the definition of EIT depletion. And what happens to EIT naught delta F? Well, this is going to be equal to EIT naught delta EI minus I T naught delta G. Okay, and we know that G is not in LP. Okay, then this is not in LP. Okay, so that's for the first one. What about the second one? So we had an F in HS that is not in HS prime, and S prime is bigger than S. Well, this will follow from the fact that the family of operators, well, it's a unitary group in HS. Okay, and since we have that EIT population of F and the norm, the Sobolev norm x2, this will be equal to, well, recall the lambda operator, lambda s, EIT delta f, and this is in norm 2, okay? And by definition of lambda and the properties, we have that is equal to EIT population of lambda s f norm 2, okay? And this is equal to, well, because we know this is an operator that is bounded, is isometry in L2, so this is equal to lambda sf 2, and finally this is equal to, well, f in norm s 2, okay, because of the definition. So if let's say EIT population of f is in H, let's say S naught of Rn, then f equal to, well, it's going to be minus IT population, EIT population of f, and it's going to be also in HS. Now, so this will tell us that if you have an f in HS, this is going to be in HS, and if it is not, it's going to happen the same. It's not going to be. Okay. Okay, a theorem about global smoothing effects. The group EIT population minus infinity satisfies. Okay, so first the integral minus infinity norm EIT f q p dt 1 over q is less than equal than c f norm 2. And the second is that integral minus infinity norm integral EI t minus t prime g, let's say t prime dt prime norm qp, okay, this is a with a dt here, 1 over q, this is less than equal than c, and the integral minus infinity of norm of g, again, well, q prime p prime dt, and all this is the 1 over q prime. And the third one is the norm of the integral from infinity minus infinity to infinity, the operation g, again, dt norm 2 is less than equal than c minus infinity g t q prime p prime dt, or 1 over q prime again. Okay, and this is all with well, we will have that p between 2n over n minus 2. This will be if n is greater or equal than 3. You will have p between 2 and infinity if n equal to, and 2 p infinity if n equals 1. Okay, and 2 over q is equal to n over 2 minus n over p. And c is a constant that depends on p and n. Okay, and always we will have that 1 over p plus 1 over p prime equal to 1 over q plus 1 over q prime all equals to 1. Okay, so this is a theorem about the global smoothing effects of EIT equation, and well, I'm not going to prove it, but basically when it's going to bound this, all these conditions appear when one apply the hard little word Sobolev theorem. And okay, so we're going to use this. So this theorem tells us that if f is in L2, then EIT of f is in LP in Rn, and this is for some p between 2 and, well, a p that depends on n, okay, of the dimension. But for example, if we have n equal to 1, okay, then p of 1, well, n equals to 1, then we're going to have that this p is going to be, well, infinity. So and okay, making the same for q, we will have that q is equal to 4. Then for f in L2, we will have that well, let's apply to this, and integral minus infinity, okay, of the norm EIT equation f is going to be infinity 4 dt 1 over 4, it will be less than equal than c f2. Okay, so this is telling us that we have an f in L2, and that implies that EIT of f is in L infinity for almost every t. Okay. Okay, so corollary, let P is not Q naught, P1, Q1 in R2, satisfying the condition of the theorem that we just saw. Then for all t greater than 0, we have that. So integral between t and 0, EIT minus t prime g q1 is less than equal to the integral of g q naught p naught dt, and this is equal to 1 over q naught prime, and c depends on n p naught and p1. Okay, so another bound for the operator EIT multiplied by function g.